everybody. I am doing a lesson on the applications of integrals, more specifically on the disk and washer method. So basically what I've done so far in the lesson is just kind of the opening exercise. We did a little bit of video so that they kind of had a background on what we're doing, and they had a visual so that they could actually see the shapes, which is really hard when we're working with volume in 3 dimensions. But basically we're going to take all the integrals that they've been working on and the definite integrals and just going, instead of area under the curve, we're now going to be working 3-dimensional. We're going to be looking at volume. So none of the topics are extremely hard. It's just more of a visual and them understanding what it is that they're doing. So what I'm about to do is an example that we would do together as a class. Before doing this example, we would come up with the integral used. All right, basically that comes from any disk that we pull out is going to be in the shape of a cylinder. And we should know from many, many years of math that we can find the volume pi r squared times the height. Okay, that shouldn't be new for anyone, maybe a little refresher because usually it's on a reference sheet for them. All right, but hopefully they can remember that. So basically we now need to get this into an integral so that we can find the volume. Well, pi we know is a constant, so if we're doing any kind of integral, we know that pi can just go to the outside. Any constants can move to the outside. Okay, and we're talking about the height. Now, we did a video on this earlier, so this will be a little bit easier for them to do. They noticed in the video that the height, if we're thinking about a washer, which we'll see a little bit later with the picture, is actually the integral that we're working on, or the interval that we're working on. So the height is just the two numbers that we're working between, which we'll just call a and b for right now. Okay, so that only leaves us with this r squared. The radius is a little bit different here because when we're talking about our picture, we have to think about where the radius comes from. And again, the video in the beginning of class will help them through this. It's a little more difficult now to explain it without having a picture yet. But we got to the point where they knew that our radius is just our function. Okay, and you know you have to square the radius, that's just part of the volume formula, and we know we're taking the definite integral of this. So we had gotten to this point already in class, so I just wanted to get it on the paper here. So basically looking at the example we have two functions, y equals x squared and y equals 0, and we're going to be rotating this around the x-axis between x equals 0 and x equals 2. So the first thing I'd want to do is give them something to look at. So we all should be able to plot y equals x squared at this point. They should all know what it looks like. Because I'm going between 0 and 2, there's no need to go into the negative, so we're just going to start here at 0. I know 0 squared will be 0, 1 squared, 1, 2 squared, 4, and so on. So we're going to have something that looks kind of like this. Again, they should know what it looks like at this point, but just in case, and we'll get a nice label there. And we also have the line y equals 0, which hopefully they can remember that that is just the x-axis. And we'll get that in there as well. Okay, so right away we know we're going to be dealing with the stuff in the middle here, right? You want to know what's in between those two functions. However, because we're rotating around the x-axis, we got to think about where else this will be. So if we're thinking about everything's up here right now, I'm rotating around this axis, it's going to end up in this fourth quadrant as well. So basically what I tell them is they can just reflect over whatever axis it is that we're rotating around. So just a rough estimate here, we can put this other graph in there, and then we just connect up our points here. Okay, so just to give them an idea of what the shape looks like, we know this is what the front face is going to look like. Okay. However, we know it's 3-dimensional, so we know we're going to have something that gives us like a little bit of a circle on the edge here and kind of show them that it starts to look a little bit like a cone. Okay, just to give them a basic understanding. Again, you can pull this up on like Desmos or GeoGebra and give them a more detailed picture, but time-wise, that would be a little hard. I guess if I had it preset, that would be a little bit easier. So basically, once they have the picture, I want to kind of explain how similar it is to regular definite integrals and doing area under the curve. So typically, we do area under the curve. We talk about those rectangles that we pull out. So you would start here, you'd go up to your function, you draw your rectangle. You would start here, you go up to your function, rectangle. Which is exactly what we're doing now, except now we're rotating around the x-axis. So these rectangles are going down here as well, and now they're becoming cylinders, okay, because now they're three-dimensional as well. Okay, so this is where our volume of the cylinder comes into play. We just need to plug it in. The only new thing for them is the radius, which we had talked about earlier. We talked about in the picture, or sorry, in the video earlier, so this shouldn't be any difficulties here. They know that the radius is just the distance from our point of rotation up to our function. So the radius is actually just our function. So when we plug everything in, I've got pi times the integral from a to b of our function squared, okay? And then you just solve this, and we end up with the volume of the function. Okay, and from here we would do an example of washers as well, and then we would get into group work.